We're going to come back to average treatment effects eventually, but first I want to take a break from that and discuss a little terminology. Now, words are just tools, but a lot of confusion is sown and a lot of conversations are at cross purposes because the same words mean quite different things to different people. So, with the aim of getting everyone on the same page, I want to discuss a few terms that arise in the discussion of causal inference making, and indeed in the context of quantitative data analysis in general. First off, we're already familiar with the idea of a treatment, sometimes called an exposure. A treatment or exposure is something that happens to some cases and not to others. It's usually the main focus of a causal investigation. So, for instance, we might be interested in estimating the effect of parental divorce on the educational performance of children. Some children experience parental divorce, they're exposed to the treatment, others remain in intact families. We then observe how many in each of these conditions fail in school. Say hypothetically that we find that there is a connection between parental divorce and failure in school, and that this connection might even be causal. But there still seems to be something missing. The putative causal effect of divorce seems to be a bit of a black box. How exactly does parental separation lead to school failure? We might find that the children after divorce tend to live with their mother, and that the mother's household experiences a severe drop in income, which means less educationally relevant household resources are available for the children. We would then say that low income is a mediating variable in the causal path between divorce and failure in school. Divorce causes low income, and low income, in its turn, is responsible for school failure. There's a minor industry devoted to statistical methods which purport to allow you to draw conclusions from this kind of mediation analysis. It turns out, however, that it's not quite as easy as some advocates appear to want us to believe. This is a very important topic, and is something that we will have cause to return to later. Anyone with an interest in causal analysis will have come across the concept of confounding. The simplest and most obvious examples tend to come from situations where we're dealing with aggregate level data. As the number of storks observed on the roofs of houses in Baltic countries increases, so the birth rate increases. Of course, we know that storks don't bring babies, and that birds build nests in spring, and that in the northern hemisphere at least, the birth rate rises in spring as well. The point is that the apparent association between a treatment and an outcome may be due to their common dependence on an antecedent variable, commonly called a confounder. The common dependence masks the fact that there is in fact no direct connection between a given treatment and a given outcome. Sometimes this is termed spurious correlation. The test for confounding is normally to control for or condition on the confounder, for example in a regression model, and observe whether the treatment and the outcome are still associated. In panel A of this slide, they're not. In panel B, T and Y remain associated, though it may be that the strength of that relationship has been reduced by conditioning on C. In the terms of our example, it may be that divorce is not causally related to failure in school, but only appears to be so because both divorce and failure in school are themselves the result of exposure to domestic violence in the family home. Sometimes we hear a variable described as a moderator, or as moderating the relationship between a treatment and an outcome. Another way to describe this sort of relationship is as a statistical interaction. Assume the moderating variable has just two values, c subscript 1 and c subscript 2. This partitions the sample into two groups. In c subscript 1, there is an association between the treatment and the outcome. In c subscript 2, there's no association. In terms of our example, we might find that in homes where violence is prevalent, divorce leads to failure in school, but where violence is not found, there's no relationship between divorce and failure. Finally, there's the term covariate. This is often used pretty loosely, and I have to confess I'm as guilty of that as anyone of doing this. In the case of a randomized controlled trial, we can usually sharpen up this definition a little. Typically, a covariate is a continuous variable x that is unrelated to the treatment variable, but is itself associated with the outcome variable. So in terms of our example, the intelligence of the child is not related to whether or not the mother and father are divorced, but intelligence has a relationship to whether the child fails in school. This leaves us, though, with a puzzle. I've been emphasizing that our focus is entirely on the causal effect of the treatment. We need to pay attention to confounders and moderators because they affect our estimate of the magnitude of the estimated causal effect of the treatment on the outcome. However, here, by assumption, the covariate is not a confounder, so why on earth are we interested in it? The answer to this is that usually we're not, but there's a good reason for including covariates in our analysis of experimental data. To see this, we have to return to the simulation we studied in Lecture 2. Here is the recipe we used in Lecture 2. Now we're going to make a few small changes. First, in step 2, as well as creating a binary variable for the sex of the subjects, we're going to create a continuous variable with values drawn at random from a normal distribution with a mean of 0 and a standard deviation of 1. Let's call this variable covariate 1. By construction, it's uncorrelated with sex and with the treatment variable. Second, in step 5 of the recipe, where we define the data generating process, we're going to use the rule y equals 0.4 times treatment plus 0.4 times sex plus 0.6 times covariate 1 plus epsilon. In essence, what we're doing here is adding an additional source of variation in y connected with the presence of covariate 1. Third, in step 6, we're now going to compare the average outcomes for the treatment and control group without and with the presence of the covariate. In essence, we do this by estimating two regressions, one that excludes the covariate and a second that includes it. Here are the outcomes for the two sets of simulations. In the top graph, we have a histogram of 10,000 replications where we do not include the covariate in the analysis. In the bottom graph, we have 10,000 replications where we do include the covariate. On average, the estimates of the treatment effect are identical and correct. We already know what that should be. It's equal to 0.4. But by comparing the graphs, it should be obvious that the spread of estimates in the upper graph is larger than in the lower graph. So including a covariate that has a substantial relationship with the outcome variable is in fact beneficial because it increases the precision with which the treatment effect is estimated. In other words, the standard deviation of the sampling distribution of the estimator is reduced, or another way of putting that is to say that the standard error is reduced.